Everybody, welcome back. I'm so excited. This is our cliffhanger. This is our fourth video in this series. So I hope you paused and you tried going backwards. I just want you to try it and let's see what process you come up with. I'm going to show you my process. You know, we made a big deal on the last video on labeling our acid in our base and then our conjugate acid and our conjugate base. I want to use those definitions to go ahead and label our conjugate acid and conjugate base, and that's going to help us track what's happening in this reaction. And then I'm going to turn around and color code. We used our mechanism to color code, and that helped us draw our product. Why can't we do that backwards? So I'm going to take a look at both of these, and right away I see charges. Your charges still have to match. So you can't have a negative and have a conjugate acid. It's just not, or a conjugate acid. It's not going to happen. You either need a negative, or I'm sorry, I just goofed myself up. You either need a positive or a neutral for a conjugate acid. So that just doesn't match with this structure. So let's go ahead and use our charges to go ahead and label. All right, our conjugate acid has to be that ammonia, that ammonium ion. We've got a nice positive charge there. And then that means that this negative has to be our conjugate base. Here's our negative. Okay, so remember which one turns into which one. Your base turns into conjugate acid, and your acid turns into the conjugate base. So how does that help us go backwards? In each one of our acid-base reactions we've done so far, what was the job of a base? It was to take a hydrogen. And where did it take it? From the acid. So our acid, that means, had a hydrogen on it, and now that hydrogen has ended up in our conjugate acid. So I'm going to color code. We formed that bond, and we left behind 2 electrons when we took that hydrogen. So then how do I draw those structures? Well, then your acid had to have that hydrogen right here. And then the base was missing that hydrogen and had a lone pair. Let's verify that by drawing our mechanism. That's exactly what we would get. I love it. So we want to take these acid-base reactions and actually be able to go in either direction. And then just for fun, just to review and practice, let's go ahead and add pKa's for both of these just to make sure we're on the right track. And then let's add our pKa. All right, we already know some of these pKa's. That's a 9.3. This one was 36. This guy is weird. Let's see if we can find it. It is phenol. Let's look on our pKa table. I don't seem to see it, or do we? Let me help. Okay, it's called phenol, and they just didn't draw out the structure. So you may want to take a pKa table and make sure you've drawn out those structures to make it a little bit easier to read. So that phenol pKa is 10. So would this reaction happen? Yeah, it'd actually be fairly even, Steven, wouldn't it? Because you just have a difference of 10 and 9.3. That's not that different. So would it happen? Yeah, it would mostly be this way, but it would be fairly even, Steven. Okay, I love it. I hope that was fun. You'll have to try some of these. They're definitely in the homework and the practice test. And just get so good at your acid-base mechanisms that you can go forward or backward. Now I want to make it just a little bit sassier. I want to show you what else our pKa table is good for. So let's take and follow our process. And let's look at this structure and see if we can find that on the pKa table. And let's look. Let's help us. Okay, that is an acetylene. Aha, here it is right here. See that triple bond? That is an acetylene. And notice where my conjugate is. It's going to be right on that carbon. So that acetylene, pKa of 26. Let's go use that. All right, now let's check our pKa table for that one. We're not going to find it. This is where you've got to draw your structures. Potassium is just like sodium. They only bond ionic. So your structure is like this. And now, do we need our pKa table for this one? No. That negative sign screams base. So here's our acid. And here's our base. Let's go ahead and draw that mechanism. There's our hydrogen, and let's leave behind those electrons. All right, we are going to leave this negative on carbon, and we just made water. Okay, we've done a couple of these making water, so that seems pretty reasonable. And then our K would be a floater here, nice ionic bond. Okay, and then let's go ahead and include our pKa of water. Our pKa of water was 15.7. We saw that in an earlier video. So if we want to draw our equilibrium arrows for this one, well, we've got a 26 and a 16. So which way does this equilibrium lie? It's actually going to lie backwards. So that's awesome, except didn't we actually learn in Gen Chem 2 that this is a strong base? Okay, that's adorable. It's a strong base in water. But for an organic chemist, that's actually middle of the road. Our strong base will never be stronger than what this pKa allows. Okay, let me say that in another way because that's pretty deep. How do we get a reaction to favor going forward? You need the higher pKa on this side, and you need your lower pKa on this side. So that means that anytime you're making water, you have to have something lower in pKa than 16. Well, look at our pKa table. We have a million things on there, and if we look for water, it's not anywhere near the top. It is in the middle. Our alcohols and our water are right smack in the middle. So what if you actually want to have an acid-base reaction with something on this side of water? It's not going to work. That reaction is going to be terrible. But yet in organic chemistry, we often run reactions that aren't in water, and we can use other reagents. So how could we create a stronger base? If we need our reaction to go this way, we need to end with a higher pKa. Okay, well, what are some things that have a higher pKa? Well, let me show you. There's 2 or 3 extremely common ways to look at our bases in our pKa table. So we need to end on this side with a higher pKa than what we're starting with on this side, than your acid, by quite a bit. So if we want to keep this same starting material, look what happens when we choose wisely and we choose another base. We have a pKa of 26. So sodium hydroxide, potassium hydroxide, anything that makes water just isn't going to cut it. But now look at this. Remember, potassium only does an ionic bond, so that means our hydrogen is actually a negative. Oh, shut the front door. This is a base. This is an acid. Now let's draw that mechanism. We have an available pair of electrons right there. Now, if we take this hydrogen, let's look what happens. We're going to actually make this deprotonated carbon. We'll still have our little K plus as a floater. And then now, what did we just make with hydrogen? Holy crap, you just made literally elemental hydrogen gas. This is an extremely common base in organic chemistry for two reasons. One, let's go grab the pKa. It's on our table. Let's go look. Let's keep looking. Holy crap, look at that. pKa 35. All right, so our base just made a conjugate acid with a pKa of 35. So which way is this equilibrium gonna go? Toward the higher pKa. So this reaction just got even better. And then when we include Le Chatelier principle and we actually start forming bubbles and we lose our hydrogen gas, it turns out that this reaction doesn't even go backwards. It is fully forwards. That's what makes it such a good base for organic chemistry. So we can get much stronger in our bases than what you've been taught in Gen Chem 2, which is sodium hydroxide, potassium hydroxide, lithium hydroxide. Our bases get much stronger. And you'll notice that they're going to rank by atoms. So if we start by if we end up making H2, if we start with one of our hydrides, if we start with, let's say, our nitrogen in ammonia, deprotonated, and we make ammonia, now we're talking pKa, oh my gosh, excuse me, 35 and 36 on our product side. So our nitrogen bases are much stronger than our hydroxide bases. And then to get even stronger, we're going to see that we can have carbon bases. That is a C minus. And our pKa on these for our carbon bases can get up to 50 to 60 pKa. They are the strongest bases out there. So we're going to choose wisely in our base and take advantage of that pKa. This is why organic chemists only need a pKa table. We can judge acid and base using the same table, and that is nothing if not efficient. I love it. So I want to leave you with one to try. And then write out what we just wrote out and see if that reaction would be better or worse than using a hydroxide as a base. All right, I'm going to leave you with a cliffhanger.